the next speaker will be Megan Berry, and she's going to talk about alpha element bimodality in fire simulations.
Here we go. Right, this sounds good. Can you hear me? Cool. Okay. Good morning, everyone. My name is Megan Berry. I'm a PhD candidate in Andrew Wessel's group at UC Davis, and I'm here today to tell you about some of my results on looking into the bimodality and alpha elements in Milky Way-like galaxies. So first, what exactly do I mean by this alpha bimodality? So hopefully many of you are familiar with this plot, but just in case you need a refresher or if you haven't seen it before, this is a plot that shows some different relative element abundance ratios in the Milky Way. So this is apogee spectroscopy data of actual stars. So each point is one star in the Milky Way. And the general idea behind this plot is to trace some of the most dominant element production processes in the galaxy, and especially those that are sensitive to events in the galaxy, such as mergers and the changes in the star formation rate and things like that. And also by alpha elements, there's a lot more to it, but basically by alpha elements, I mean those that are those elements that core collapse supernovae, type 2 supernovae mainly produce. So these kind of even numbered elements like oxygen, magnesium. Tracing the galactic elements, the element evolution of the galaxy, the two dominant processes are these two types of supernovae, core collapse supernovae or type 2 and white dwarf supernovae or type 1. There's a lot of other interesting stuff, other interesting element production processes, but in terms of just like sheer amount of the elements produced and the frequency of these events, these supernova types are what dominates the galaxy-wide patterns that we can see. So this x-axis here is iron over hydrogen, and that you can loosely think of this as like time gone by, as we would generally expect iron to build up over time, generally speaking. And then this vertical axis, again, generally speaking, there's a lot of like complicated processes that go on with this, but you can sort of think of this as a ratio of how many of each supernova process has been going on in this star's, in each of these stars' environments. So with the alpha elements being mainly from core collapse, although those do produce a bit of iron, and iron primarily from white dwarf or 1A supernovae. So what we would generally expect to see just in theory is the oldest stars you would imagine being on the top left of this plot, being of course not having much iron, and then early on in a stellar population, you know, we start off with core collapse, and then it takes some time for the white dwarf supernovae to kick in. So we expect the oldest stars to be on the top left, and then as iron builds up and as more and more white dwarf supernovae occur, we expect it to gradually move down and to the right. And we do sort of broadly see this in the Milky Way, but something that is was not expected or predicted and still not really explained is the fact that there are these two populations, these two separate populations in this like element abundance space that I'll call the high alpha and low alpha population. Yeah, so it was not predicted. It's not known why this is like this. You know, was it because like some merger came in and reset the element abundances? Is it some like stellar evolution process? We're just not sure what this is, but just because the element abundances in these stars are kind of like a history of what's happened in the Milky Way. If we can figure this out, we can maybe figure out information about past events, like maybe a GSE merger, something, disk formation, something like that. That was kind of a lot of background, but I think this plot takes a lot of motivation because it's kind of obscure. But so the main questions that this data begs is how common is this feature among Milky Way mapped galaxies? Like, we only have this data for the Milky Way, basically, just starting to get it for Andromeda. But is this common? Like, does this represent a broad common process among galaxies, or is it rare? Is this a special feature of the Milky Way? Right now, we don't know. And also, just what causes the existence of these two populations? I'll also point out it's pretty well known that the high alpha population is associated with the thick disk of the Milky Way, and the low alpha population is associated with the thin disk. So we do know that much. But especially just if we can figure out what caused this, maybe we can learn something about the Milky Way's disk formation, maybe GSE merger. Still don't know. So that's what our goal is by looking at this feature. So here are our bimodal galaxies from the FIRE simulations. So we are not, FIRE is definitely not the first simulation group to have examined this. There's several other simulation groups, both cosmological and idealized, that have observed this feature in their simulations. But we are perhaps, maybe arguably, the first to offer both simulations that are cosmological and high resolution enough to resolve the thin disk, and to have enough galaxies to look at to comment on the prevalence of this feature. What I've found is that, right off the bat, my first kind of result is that we found about a quarter of FIRE galaxies display what I'll call a strong bimodality. So there's kind of possibly a future paper is this. There seems to be kind of degrees of this feature, like, but just as a limiting case, I'm only looking at ones that have this clear separation between the high and low alpha populations. So we find that this is about a quarter. So not common, but not rare either, which seems to be kind of a pattern among Milky Way traits. But let's also try to get to the bottom of what is the origin of this feature in these galaxies. So I have an animation here I'll play in a second, and a lot's going to happen really fast, so I'll do my best to describe it. So in the top right here, this is just which galaxy it is. This is the redshift 0 element abundances of these stars, and this line I've drawn to separate the high and low alpha populations. And then on the left here, you will see in bins of stellar age at redshift 0. So this is all redshift 0 stars, but just binned in terms of their age, starting with oldest to youngest. You can see this, the kind of path that this will take through this element abundance space. And on the bottom right, you'll see the location of these stars in the disk from like a side-on view. Right, so here we go. So as we expect, it starts off in the top left, gradually moves towards the bottom right. And then something happens there, and then very suddenly, stars start forming in that low alpha. Stars start forming in a disky pattern down here. So let's, I'll play that again, and let's focus on the disk this time. So you'll see it starts off in high alpha, and then right when this crosses this line, very suddenly, the disk appears. So in this case, and in the case of one other of our 4 galaxies, the time at which the path crosses from high to low alpha is basically right when the thin disk forms, or right when you start to see like disky features in the galaxy. So let's go back and back in time in the simulations and see like what happens at that time when the plot goes all kind of crazy like that. So right before what I'll call the alpha transition, when it goes from high to low alpha, you can see a very gas-rich merger coming. Yeah, and also I'll point out that there's very little gas in the galaxy at this time. Like this is zoomed in on like the actual host galaxy, but it like appears that there's more gas in this satellite coming in. But anyway, there's this merger comes in. This merger comes in during a period of there being kind of depleted gas in the host galaxy. Then you can see, in both of these, there's no disk to really speak of in the host galaxy. This is during the merger, the gas is just going everywhere. And then very soon after, 20, 30 million years after, you get this really nice disk. So just very sudden disk formation after this merger, and exactly at the time that the galaxy transitions from high to low alpha. And we saw basically the same thing in 2 of the 4 galaxies that we looked at, which is also pretty interesting because it's kind of a clean effect that happened in both of these. But then what about the other 2? So it's starting to look like there are multiple ways that this can occur, and that kind of agrees with other works on this topic where there's still not any one explanation. So it could be, there's different ways to get this feature. Yeah, I'm doing on time. So I'll play this real quick. So this is another one, and this one, the disk starts to form before the alpha transition. I won't spend too much time on this, but that is pretty, that's kind of not expected. Like the disk, it definitely complicates things that we seem to, I'll play this one more time, that we get this disky behavior before the transition to low alpha. And this and the other galaxy are like this. So we have 2 where the thin disk, or just broadly disky behavior, occurs basically at the same time as the alpha transition, and 2 where the disk forms first and then there's the alpha transition. So this is the star formation rate. There's other ways we can track the diskiness, but you can see this is just the star formation over time. This green line is when the path through that element abundance space crosses from high to low alpha. And with these 2, it's basically right when the star formation rate drops significantly, presumably by just the disk kind of the rapid formation of the disk kind of slows the star formation rate suddenly, and causing a sudden difference in the element abundances. And then these 2, I'm still investigating. Unfortunately, I don't have a solution for this quite yet. Still in progress, but it's really interesting that you can see, the star formation rate. And I have looked at this. This does coincide with the appearance of the disk, but the low alpha transition doesn't occur until after that. So I find that there's at least 2 ways for this phenomenon to occur, and this is still, I'm still trying to figure out what happens in these galaxies to cause such a sudden drop. But it's not the formation of the disk. Yeah, so to summarize, in our first case, we kind of have our story of where the host galaxy is in a period of very low gas. A merger comes in and kind of feeds the disk and keeps star formation, or causes the sudden appearance of a disk, which slows down the star formation rate suddenly. And then the other 2 that drop to low alpha after the disk has already formed, which I'm still looking at. And then also that we find about a quarter of these galaxies have this feature, at least a strong version of these features. There are more that are kind of borderline. So it's not common, but it's not rare. Okay, thank you.
Okay, questions for Megan? So, have you started to look at the interstellar medium and the circumgalactic medium to see where the metals are that will form these stars? Presumably that's going to help to answer your question of how and why it's happening.
Curiously, possibly curiously, the average value of iron over hydrogen kind of stalls out, it stays constant for these later stars instead of increasing like you might expect. I'm still looking into that as to if it's disproportionate loss or yeah.
So the standard fire picture seems to be that there's a sudden transition to a very thin disk, which occurs when the inner certain galactic medium virializes. So that presumably, even though you didn't find that the transition to low alpha from high alpha occurs exactly at the formation of the disk, but that must have something to do with the element abundances in the thin disk, because that's the gas that's forming the thin disk.
I think what the explanation we've been going with is that I've looked at the relative supernova rates, and right before the drop, there is a big increase in white dwarf to core collapse. Like there is like a significant spike in white dwarf supernova to core collapse supernova rate. So that's kind of what we think is just, the star formation slows, so you get less core collapse, and then the white dwarfs have, built up, or I guess the predominant effect would be the core collapse slowing. Yeah, that's what we've looked at so far. But yeah, I'm still looking at like inflows, outflows.
Yeah, so I'm trying to understand. I mean, you described what was happening as a drop to low alpha, but the way I learned this back in the Dark Ages was that, it's not that the alpha abundances are going down. It's that the alpha abundances rise first because the type 2 supernovae feed back quickly, and then it takes a while for the iron to catch up because that's coming out of type 1As, which have a long delay time. So is it in fact the case, I mean, so you described it repeatedly as the alpha dropping, but if you look at alpha to hydrogen, is that actually dropping, or is it just that the iron is rising?
Good question. So that was more my language. When I said alpha dropping, I meant like going from high to low. Like I did specifically mean like alpha over iron. But I have looked separately. Here, I have looked separately at the amounts of magnesium and iron. These are like adjusted. They're not actually the same, but you can see like if you start them the same like before, they eventually end up diverging. And this is what I was talking about, where like iron kind of flattens out. But like magnesium, I guess it flattens out. Yeah, it almost seems like magnesium goes down in a lot of cases, which is why I'm looking at the inflows, outflows. Like maybe it's getting disproportionately like blown out or something like that.
So is this basically that you're just blowing away the entire ISM and then replacing it with a new lower metallicity one, and that's why the magnesium abundance is dropping?
I think it's more to do with the slowed star formation rate, because I've looked at the properties of the satellite, and the satellites are obviously like way lower in iron over H, but the magnesium over iron of the satellite is actually pretty similar to that of the host galaxy. So I think it's looking more like the vertical gap that you see in the plot is from something to do with the star formation rate. And these are the supernova relative rates, where you can see like during this there's this spike kind of before with the merger, but like also during the transition period it goes way up.
Okay, so while the next speaker is setting up, we have time for one quick question.
David Koo, Santa Cruz. I wanted to ask for recycled gas from the host galaxy. Is that typically high alpha or low alpha? Because I imagine if it's blown out, there's no more stars to give it additional iron later on, and so it would be high alpha is my guess. Do you have a feeling?
We haven't done any specific tracking of inflows and outflows, more just, or the next thing I'm going to do is just like broad patterns in like the metallicity of the gas coming in and out, just mainly to focus on just this galaxy-wide property. But yeah, we have looked at like the metallicity of the gas over time and the mass of the gas coming in and out. I don't know if that.
Okay, thanks, Megan.